All right, so you've been looking at logarithms with different bases. On your calculator, the log button is actually what's called the common logarithm, which is the log of base 10. So anytime you see just log of x, that actually means log base 10 of x. Your calculator only does two logarithms. One is the common logarithm, and the second is the natural logarithm, which is base e. So we don't write log base e of x, we actually write it ln, which means natural log. So we have log of x, that means it's got to be base 10, or we have natural log of x, which means it's got to be base e. The issue is, if I'm dealing with things that are not base 10 or base e, what do? Well, we've got this change of base theorem, and you do have to have this theorem memorized. So as long as your bases are not equal to 1, what you can do is if you have the log of any base, what you do is say, okay, well, I'm going to change that to either base 10 or base e, and I'm going to take the log base x, that's this number here, divided by the log of the original base that I had. This also works with natural log, and I'll show you some examples. One thing that I'm going to point out right here in the beginning is that when you're working with logarithms, you're often dealing with decimals to a lot of decimal places. Don't round anything until the very end, and it's in bold-faced, but I'm going to just underline it in pink, because what happens is you get errors that give you an incorrect final decimal place. So wait until the very end before you round. You don't want to work with rounded numbers. So now we're asked to evaluate the log base 4 of 20. So what we'll do is we're going to use the change of base theorem. And we're going to say that the log base 4 of 20 is equal to the log base 10 of 20 divided by the log base 10 of 4. And actually, I put that directly into my calculator exactly the way that you see it. The log button is all the way on the left next to the 7. And as we've done in the past, make sure that you put parentheses around the entire numerator and then around the entire denominator. But when I do this, I get 2.161. This problem can also be done with the natural log. We can do natural log of 20 divided by natural log of 4. And I can put that in my calculator as well. The natural log button is directly underneath the log button in my calculator. And the awesome thing about this, hopefully you're putting this into your calculator as well. The answer is the same. 2.161. Let's take a look at the next problem. Log base 2 of 0.7. So I'll start with log base 10 of 0.7 divided by log base 10 of 2. And I'll put that into the calculator. On this one I get negative 0.515. Doing the same problem with natural log, I can take natural log of 0.7 divided by natural log of 2. I put that into my calculator, and amazingly enough, I get the same answer. You should probably put these into your calculator if you haven't done so already, so probably pause the video, put this information into your calculator, and then pick back up on the video. For the rest of these slides, we're pretty much going to be doing word problems that deal with the common logarithm and the natural logarithm. They use a lot of different formulas. These are formulas that I will give you on a test, so you don't have to have them memorized. But the pH formula on page 447 is this. And you're probably like, what on earth does that mean? H3O plus is the concentration of hydronium ions. So now that you know that, we're going to use that formula. We're going to put this in place of this, okay? So the pH is the negative log of 6.8 times 10 to the negative 8th power, right? That's scientific notation. Just going to plug that right into the calculator. And I get a pH of approximately 7.2, or I guess we can say 7.17. So that means that we're slightly more alkaline than water. We can go backwards with this, right? So if we have the pH given to us is 4.3, how do we find this number? Meaning, how do we unlog this? So we have 4.3 is equal to the negative log of this ion, H3O+. Well, we actually unlogged things in the first section that we did. So remember, we're at base 10 here. So first thing we'll do is we'll get rid of this negative. We'll divide everything by -1, and we have negative 4.3 is equal to the log base 10 of H3O+. Now, to unlog, we just use exponents. My base, remember, base 10. So I have to the power of negative 4.3. Now, this really isn't the way that we give an answer, so we'll actually plug this into the calculator to get a better answer. And when I do that, I actually get the concentration of ions is equal to 5.01 times 10 to the negative 5th power. The last thing is this classification of wetlands. You'll probably see that in some of the problems that we work on. But that's on page 448, and there are different kinds of wetlands. There's bogs, fens, marshes, and swamps, and it depends on what the pH level is. So we have this hydronium ion concentration. We have to classify the wetlands. Well, first thing I need to do is find the pH. So that just goes into the calculator. And the pH is 2.347. So I look on this list and I find out that if the pH is less than 3, if it's 3 or less, this wetland is a bog. Got a decibel formula on page 449. I is the intensity. I naught is the first intensity, which is typically very, very faint, called the threshold sound. So we look at these ratios in order to determine the decibel level. So our intensity, our I, is this. So really, we're just plugging it in. Great thing about that is those cancel. And I plug that into my calculator. The decibel level on this is 70. All right, the age of a rock formula. That's 1 plus 8.33 let me erase that. 1 plus 8.33 times a over k over the natural log of 2. So here we're told that a and k are equal to each other. A and k, by the way, are the number of atoms of argon 40 and potassium 40. But if those values are equal, then a over k is 1. So we've got the time is 1.26 times 10 to the 9th times the natural log of 1 plus 8.33 over the natural log of 2. And I plug that into the calculator. I make sure to put parentheses here and here. And my calculator has given me this number. So I'm going to remember back to 3rd grade, put in a comma, right? So I've got thousands, millions, billions. So we could call this like 4.06 billion years. We can do this again where we're given the ratio between argon 40 and potassium 40 as a decimal. It's really not going to change much. Again, I'm going to be very careful with my parentheses in this problem. And again, I get this number. So I'll say that it's 2.38 billion years. So if you look on page 450, about halfway down the page, it talks about radioactive forcing. What happens is when carbon dioxide in the atmosphere traps heat from the sun, that additional solar radiation is what's called radioactive forcing, and it's measured in watts per square meter. We actually call this R, and the formula is R is equal to K times the natural log of C over C naught. C naught is the pre-industrial amount of carbon dioxide, and C is the current carbon dioxide level, and K is going to be a constant. So looking at this, I get R is equal to K being 14 times the natural log. C is equal to 2C naught. 2C naught over C naught. Those will cancel. So R is equal to 14 times the natural log of 2. So when I plug this in to my calculator, I get R is equal to 9.704, and it's watts per meter square. We can also use this to find the average global temperature increase to the nearest Fahrenheit. The formula for this, T sub R, is 1.03 times R. So we figured out R already. That's here. So we can plug that in. When I plug that into my calculator, I get approximately 10 degrees Fahrenheit. All right, next problem, modeling diversities of species. So when we look at that, the formula is this. And actually this will continue depending on how many species there are. So what you need to understand is what these numbers actually represent. This P sub 1, in this case, is equal to the amount in species 1 divided by the total amount there are. So there are 160 plus 140, which is 200. And then P sub 2 will be 140 because there are 140 divided by 200. So what I'll do is cancel these out a little bit, make them some reasonable numbers to work with. 6 over 20 would be the same as 3 over 10, so that's 0.3. 14 over 20 would be the same as 7 over 10, so that's 0.7. So I have h is equal to negative 0.3 log base 2 of 0.3 plus 0.7 times log base 2 of 0.7. Now I'm hoping that you're looking at this going, Ms. Busselmeyer, didn't you just say that we can't really put logs to any base other than e or 10 into our calculator? I did say that. So now you actually need to do some change of base formulas. So log base 2 of 0.3 is going to be log base 10 of 0.3 over log base 10 of 2. And then log base 2 of 0.7 will equal log base 10 of 0.7 over log base 10 of 2. So I'll actually put these into my calculator first and then substitute that in for these. So I've got the first one, log base 2 of 3, is negative 1.737. And then log base 2 of 0.7 is negative 5.515. And now this gets put into the calculator for the final answer. Now when I put this into my calculator, I don't use these rounded values. I actually put this into the calculator so that I have more exact values. So there are a lot of parentheses that are going to happen, and that'll take some practice. But once I've done all that, I get 0.881. So that's going to be the measure of diversity of the species. Now, your favorite and mine, you have to do a logarithmic regression. And I even give you the hint to use lnreg on your calculator for the data. So remember that it's stat. Number 1 is edit. This will be L1, this will be L2. Then you will quit. You will go back to stat. S-T-A-T, oops. Let's try that again. It's just stat. Stat. You're going to arrow over to calc, and then you're going to go down to lnreg. And that's going to give you a linear regression, and that's what I want to see. I'm sorry, a logarithmic regression. That's what I want to see for this.